Welcome back to Pentagram Prime, everybody. Today's lesson will be how to solve this thing. I'm not really sure what to call it because I've never seen a real title for it. I've seen it in an integral table, but it's basically the integral of 1 over a plus b cosine theta plus c sine theta. And not using the pen as much because the camera is a little more steady when I hold it with both hands. We will be doing this using Weierstrass substitution. And let's jump right in. So Weierstrass substitution basically involves taking the variable t and setting it equal to tangent tangent of theta over 2. And what you get are these groovy little things that turn your thetas into t's. Sine theta equal to 2t over 1 plus t squared. Cosine of theta equal to 1 minus t squared divided by 1 plus t squared, and of course d theta equal to 2 dt over 1 plus t squared. So I've heard this referred to as kind of an exotic methodology. Supposedly doesn't even get covered in most calculus courses. But I was interested in playing around with it for fun because a lot of integrals do fit this form, and I wanted to go see how it solves. I want to caution the audience repeatedly. I will pause to do this. There is a reason why you don't see too many lessons on how to solve this integral in its general form with just the constants laid out like this. I didn't even get into what happens when you have a multiple times theta, like omega theta or a theta or anything like that. Basically, the general solution that you're going to get, well, it's not a general solution. Once again, sorry about my air conditioner. A and B, if they are equal, this just won't work. So keep that in mind. Consult an integral table if necessary. So this doesn't really give you a general solution. But moving on, we're going to substitute in for d theta and for cosine theta and sine theta. And now we've lost all of our thetas, and we now have t's. And basically these terms, they actually you gotta multiply times 1 plus t squared, and then cross this out, and now we have this nice little fruit salad thing down here, a, b, c, and we need to go ahead and sum up the the terms for t squared, and I think there's only one multiple here for t. And what you come up with is a standard quadratic. We have a value for the t squared term, the t term, and the constant. And we pulled 2 outside of it. I apologize, I'm moving my 2's around so it almost looks like it's in the denominator, but it is in the numerator. So at this point, we're going to go ahead and take the denominator, and we're simply going to complete the square using our formulas for the quadratic, using quadratic formula. And then we end up with a new expression for the in place of t squared, and I shouldn't even say in place of t squared. Also, some of you might not know what it means to complete the square, so there you go. Always helps to have these things. I like to keep this one memorized, but some people might have to go look it up in a book. Anyways, we have we have basically a squared term here, and this thing becomes a squared term over here, although I haven't done it in this step. But basically something squared plus a constant multiplied times another constant. And then we'll work this a little bit as we put it back into the denominator. A minus b times t plus c over a minus b, quantity squared. plus a plus b minus c squared over a minus b. And then if we factor out the a minus b term, what we come up with is we get a minus b squared on the bottom. If you do the algebra going from this term to this term, it will work out, done multiple times. And our next step is to do a u substitution. So on the next page, we're going to substitute in u for t plus c over a minus b, which is what we have here. And of course, this just gives us a simple du equal to dt. All right. Hope nobody here is prone to epilepsy because my camera is shaking a bit. So we basically the same. We have the u squared term over here, and then when we come over to this side, we take the exponent of a minus b and pull it outside, turn the top piece into a square root. So now we have a square plus a square. And then we're going to go ahead and do another substitution. So we're going to call k u minus u times a minus b over root a squared minus b squared minus c squared. And we're showing another example of why this will not give you a general formula, because if this quantity is less than 0, then well, you're not going to have a real solution, so it's just not going to work. As with all substitutions, we try to get a expression for one variable in terms of the other. So du equal dk times root a squared minus b squared minus c squared over a minus b. And then, of course, we have the u. So when we substitute these terms in, top and bottom, what we have is a nice little constant that comes outside. A little bloated, this formula appears to be, but we're almost there. And we'll find that this is going to factor out a squared term, and the same one that we have squared over here. And then we have this quantity squared on the bottom, well, basically two of them. So this cancels with one of these. And then we have a nice familiar looking integral over here. And this will work for certain values of a, b, and c, but as I have already said, it will not work all the time. Depending on the values, you may end up with a logarithm. Long story on that. So we come down here, and now we have 2 over a minus b divided by root a squared minus b squared minus c squared divided by a minus b. And this cancels with, and in the wrong place, this. And the end result is 2 divided by root a squared minus b squared minus c squared times arctangent of k, which of course is a integral of arctangent of k is the indefinite integral of 1 over k squared plus 1. And in the home stretch, we're going to go ahead and substitute back in for ku and t. We're going to first fill in for k, which is u over a minus b divided by the radical. And yes, I am skipping the integration constants because I didn't feel like writing them down over and over again, and neither do a lot of people. Next, we're going to substitute back in for u, which is equal to t plus c over a minus b. And then down here we have we substitute back in for t, which is tangent of theta over 2. So my camera's memory is running out, so I need to tidy this up quick. This is not a general solution. If you consult an integral table, you will find out why. But basically, for this type of integral, for certain values of a and b and c that do not violate the issues with the radical or a minus b in the denominator, this will work. And I've actually used this formula to error check a solution. Doing 2 publications on before and after midnight, so look for a KSP video about 2 hours after this one. Till then, this is Pentagram Prime signing off.